Okay, now we'll learn some special lattices. That is, first one is complete lattice. A lattice L, okay, a lattice L is called a complete lattice. Is called a complete lattice. Lattice, okay, lattice. If each of its, okay, if each of its non-empty subset has greatest lower bound and least upper bound, every finite lattice must be a complete lattice. So what is a complete lattice? A lattice L, okay, the lattice is L. A lattice L is called complete lattice if each of its non-empty subset has greatest lower bound and least upper bound. So we have learned what is greatest upper bound and greatest lower bound and least upper bound in the previous videos, that in the first video of this, okay, in this section, okay. So you can learn from that what is greatest lower bound and least upper bound, and if a lattice L contains greatest lower bound and least upper bound in its non-empty subset, okay, in its non-empty subset, then we say it is a complete lattice. Now bounded lattice. What is bounded lattice? A lattice L is said to be bounded if it has both lower bound and upper bound, okay, if it has both lower bound and upper bound. What is bounded lattice? A lattice is said to be bounded if it has both lower bound and upper bound. If L is a bounded lattice, then A belong to L and 0 less than or equal to A less than or equal to 1, okay, that is L is bounded lattice, then A belong to L and A lies between 0 less than or equal to A less than or equal to 1. And also we have A or 0 is A and 0 is 0, A or 1 is 1, A and 1 is A. Okay, so if it satisfies these four conditions, then it is called as bounded lattice. Bounded lattice, if you take R, A or 0 is A and 0 is 0. A or 1 is 1, A and 1 is A. Okay, that is the definition of bounded lattice. Then we are going to learn distributive lattice. A lattice L is called distributive lattice if it satisfies the condition. What is the condition? Let me write that here. For distributive lattice, the condition is A or B and C is equal to A or B and A or C. Then A and B or C is equal to A and B or A and C. Okay, if it satisfies these two conditions, then we say the given lattice is a distributive lattice. Then we will learn complement lattice. Okay, complement lattice is defined by, okay, now complement of a lattice we are going to define, right? Let L be a bounded lattice. So we learned what is bounded. Here L is a bounded lattice with the lower bound 0. Okay, the lower bound is 0. This is LB, right? So we say with the lower bound 0 and UB 1 with upper bound 1. Lower bound is 0 and upper bound is 1. Let A belong to capital L. The element X belong to L is called complement of A. If A and X is equal to 0, A or R is equal to 1. That is A and X is equal to 0, A or X is equal to 1. Okay, that means least upper bound is 0. Sorry, lower bound, LB is lower bound. Lower bound is 0, upper bound is 1. Then for any X in L, okay, then for any X in L is called complement of A. X is called complement of A. Okay, X is called complement of A. X is called complement of A. What is complement? If you take AND, value is 0. If you take OR, value is 1. If you take AND between those two terms, then you get the lower bound 0. Then you get lower bound 0. If you take OR, then you get upper bound, that is 1. Then we say A and X are complement to each other. A and X are complement to each other. Okay. Okay, now let us learn complemented lattice. A lattice L is said to be complemented if it is bounded and every element in it has at least one complement. So just now we learned what is bounded lattice. So a lattice is a complement lattice, or a lattice is a complemented. Is said to be complemented if it is bounded. First of all, it should be bounded, and then every element should have a complement, and every element in it has a at least one complement it should have. Okay, at least one complement it should have. Then just now we learned what is complement, right? Complement and bounded, everything we learned now. So if it satisfies bounded and complement for every element, then we say it is a complement lattice. Prove that every chain is a distributive lattice. This is the next theorem. The proof is we have to prove every chain is distributive. We know what is distributive. Now we know what is distributive. Now what is a chain? Chain is nothing but every pair of element is comparable. Comparable means if you take any two elements, either for example, if you take A, B, C, comparable means A less than or equal to B, or B less than or equal to A. Okay, or A less than or equal to C, or C less than or equal to A. Likewise, we can compare the elements. So if any two elements or every pair of element is comparable, then it is called a chain. Okay, so now we will go into the proof. Let L less than or equal to be a chain. Let A be C element of L. Case 1, A less than or equal to B, or A less than or equal to C. Every pair of element is comparable. So this is by the definition of chain. We can write like this. Now let us take this A less than or equal to C. A less than or equal to B or C. Why? Because A less than or equal to B is already there by definition. Also we have A less than or equal to C. So by theorem we have A less than or equal to B means A and B is equal to A. Okay. So here first we take these two cases, A less than or equal to B, A less than or equal to C. So A less than or equal to B or C. Okay, first thing we are doing is combining these two, A less than or equal to B or C. Now we apply this. A less than or equal to B means A and B is A. So you see A less than or equal to B. A less than, what is B? B or C. If A first term is less than or equal to second term, if you take AND operation, then that is equal to the first term. A less than or equal to B means if you take AND, A and B is equal to A. So this is what we are applying here. Okay, we are applying here. A less than or equal to B or C means A and B or C is A. So this property we are applying to this. A and B is equal to A and B or C is equal to A. Now A and B or A and C is equal to A or A. So how do you get this? So now once you consider this, you see we have A less than or equal to C and also A less than or equal to B, right? So here using the property A less than or equal to C means A and C is equal to A. A less than or equal to B means A and B is equal to A. Since we have A less than or equal to B, A less than or equal to C, we have A and C is A and B is B. So A and B is A and C is A. So A or A. You can substitute these two values. A or A is equal to A. This is equation number 2. So you see equation number 1 and 2. From these two, we get A and from this one we get A and B or C is A. So here LHS is equal to RHS. Both the RHS are equal. So you can equate the LHS. A and B or C is equal to A and B or A and C. So this is the first case we have proved. Now we take conversely. A less than or equal to B can be A greater than or equal to B. A less than or equal to C can be A greater than or equal to C. Because chain means every pair of element is comparable. Comparable means either A less than or equal to B or B or A greater than or equal to B. Similarly, A greater than or equal to C. So now let us consider case 2 now. So considering this, we write B less than or equal to A, C less than or equal to A means B or C less than or equal to A. So combining these two, we can write B or C less than or equal to A. Okay, now we have a property. A less than or equal to B means A and B is equal to A. So here also you have less than or equal to. So if you take AND property, you will get B or C. If you say A less than or equal to B, if you take AND between these two elements, that is equal to the first term. Similarly, if you take AND between these two elements, you will get the first term. B or C and A is B or C. Or you can rewrite it. You can write A at the front. A and B or C is equal to B or C. This is equation number 3. Now we take these two equations once again. B less than or equal to A implies B and A is B. Or by commutative A and B is B. You can interchange this. A and B is B. So this is by consistency law. B less than or equal to A means B and A is B. Similarly, take the next one. C less than or equal to A. C less than or equal to A means C and A is C. Okay, by that law we get C, by consistency law C and A is C. Now C and A can be written as A and C. You replace this, interchange. A and C is C. Now these two, you combine these two. A and B or A and C. Okay, A and B or A and C is B or C. Okay, you take or between this and the next equation. So you get B or C. This is equation number 4. Now 3 and 4, you see RHS is equal. B or C, B or C. If RHS is equal, then LHS will be equal. That is A and B or C is A and B or A and C. So we get from 3 and 4, A and B or C is equal to A and B or C is A and B or A and C. Now using duality in both the cases, the other form of distributive law can be obtained. So this is the distributive law. If you want the other form, you take duality. Duality means AND will be replaced by or will be replaced by AND. So you get, you see, A or B and C is equal to A or B and A or C. So just interchange, you get the law. So now distributive property. So we say distributive property is also true. Therefore, every chain is a distributive lattice. We assume the given lattice as a chain. Okay, we assumed L as a chain. That is, every pair of element is comparable. Then we prove the distributive condition so that the lattice is a distributive lattice.